Okay, so today let us just revisit the last theorem that we stated at the end of the previous lecture, which is the Cantor-Schroeder-Bernstein theorem. So this theorem usually is called the Schroeder-Bernstein theorem, but some textbooks also call it Cantor-Schroeder-Bernstein theorem, because this was the statement was proposed by Cantor, and then the proof was given by Schroeder and Bernstein. So this is the statement of the theorem, which is already written. Let f be an injective function from A to B, and G also an injective function B to A. Then there exists a bijective function H between A and B. Okay, so this might seem like not so difficult statement to observe, but one thing that is important is it might be the case that F and G are not surjective. Right? Just because there are two maps that are injective, why should there be one map that is both injective and surjective? In all probability, like G need not be the inverse of F. Right? So you have like two sets, right? A and B, and you have a function F from A to B, which is not surjective. So there might be some portion here that does not have a image. And G is another function from B to A. So there might be some things here that do not have this. So why should you be able to construct a map between A and B that is both injective and surjective? But supposedly you can. That is what the theorem tells. So before we see a proof of this, what are some nice applications of this? So if you remember, we wanted to show in the Cartesian product of n with n is contained. And one of you actually came up. So is this comment about the reference that Milan gave, or is it about what we are doing?
Yes, reference that Milan gave.
Okay, yeah, I haven't seen that, so maybe Milan let us know. So this, the Cartesian product of n and n being countable, we did see a proof, we did see an idea. We will come up with a function f, which takes in two natural numbers and spits out one natural number. So this function we saw is injective and is not surjective, in the sense that anything divisible by, that is not divisible by 6 will not have a image. So, so this is a injective function from n to n. Now, can someone try to define a function from n to n present, an injective function, like the most straightforward way, G, which takes in n.
One thing could be quotient and remainder with respect to some integer.
It's like what integer? Not even that, right? Just fix one of the coordinates to be n and the other thing is n. So you must remember that Cartesian products are ordered, right? So even this is right?
Yes, yeah.
Right? So g of n1, if it's equal to g of n2, then it must only be the case that n1 is equal to n2, because Cartesian product is an ordered, it's a set of ordered pairs. So this is an injective function from n to. And now, if you actually had to come up with a bijective function between the Cartesian product of n and n to n, to the set of natural numbers, it would have taken a lot of time. But now, because we have two injective functions from the Cantor-Schroeder-Bernstein theorem, we know that there is a bijection. There exists a function h from n cross n that is bijective. This means that n cross n is countable. The Cartesian product of n is countable. So this is probably one application. Another application of this is For example, I had posed this question sometime back. So if you look at the real interval, right? Is the open interval 0, 1 and the interval. So if somebody had asked you what the coordinate of these two sets are, like is it equal, not equal, and so on, initially it might seem a bit difficult, right? Because any function that you define from 0, 1 to 0, 1, like one might not have a pre-image, the other way around also it might become difficult to actually explicitly construct a bijection. But now with Cantor-Schroeder-Bernstein theorem, this seems like super easy. So what do we have to do? We need to construct an injective function f from this interval 0, 1 to 0, 1. Can someone come up with a function?
F of x equal to x.
This is an injective function. This the identity. Just that one might not have a pre-image. But now you have to come up with another function g, which is from 0, 1 to 0, 1. That is also injective.
G of x equal to x by 2.
Right. So this function is injective. Now from the theorem, we know that the cardinalities of these two intervals must be the same. Okay. So even these simple statements, right, which seem difficult to prove earlier on, with this theorem, seems to be like super easy, right? Because it's always easy to
I have a doubt.
Uh-huh.
With the function g of x equal to x by 2 from 0 to 1 closed interval to 0 to 1 open interval, we can directly claim that there is a bijection, right? Because every element is
So this is
mapped.
0 is open and 1 is closed. I don't know if you observed that.
Yeah, 0 is open and 1 is closed. So 1 will be mapped to 0.5, and
Right.
all the other things will have one mapping each. So as a result, it is already bijective, right? Like irrespective of this theorem, G is already bijective, right?
You're saying that it is sufficient to show, just demonstrate G?
Yeah,
I mean, it's not
just
only
with G of
injective,
x
it's
equal
also.
to x by. What, ma'am?
Yeah, I think that's because 0 is not included.
Yeah, yes, ma'am.
Right. Yeah. No, but there might be some other places where like 0 might be included in the interval.
Oh,
The
yeah,
closed,
yes, ma'am.
like
Yes, ma'am.
yeah, closed interval 0, 1. I should have picked that as the example. All right, this is also bijective. That's what it says. So this already demonstrates, so it's not necessary to apply the theorem. That is true. Okay, but one thing to remember, it's always easy to come up with injective functions as compared to constructing bijections. Right? Even in the case of rationals, right? We had this diagonal argument, which seems easy to show that the function is injective. But to show that every rational number appears somewhere in the list, these things are what make things like difficult. So now with this theorem in mind, it's enough to like demonstrate two injective functions. So one thing I actually want to give you an overview of this proof, given that it's a very historic proof. So Cantor actually proposed this theorem, though he was not able to give it. Sorry?
Ma'am, could you wait a bit? I didn't understand how G is a bijective function.
Yeah, what is the supposed pre-image of 0.9 then?
Anything above 0.5 does not have pre-image.
Yeah, that is because G inverse is can at most be 2.5 or something, 0.5, right? So maybe we should try to construct inverse of this. So then 0.6. This is not. I mean, it will be
Yes,
like
ma'am.
1.2,
Yes, ma'am.
which 1.2,
Yeah, I
which
just
is not
figured
in
it.
this interval.
Correct.
Yeah. Sorry. So this is fine. This is a fine example to demonstrate. Okay, so Yeah, so Cantor proposed this theorem, and surprisingly, he could not find a proof of it, or I think he wrote even incorrect proof, which was later corrected by Schroeder and Bernstein. So most textbooks call this the Schroeder-Bernstein theorem, although the statement was actually given by Cantor. So this is another way of saying that if the cardinality of A is less than or equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, then both these sets should have the same cardinality, which is what we would have done generally with numbers. But with infinite sets also it is true. So now to actually demonstrate a proof of this, which is quite involved, not very involved, but yeah, it's a very nice proof to see. Okay, so to do this, I want to actually introduce something called, so the proof you can find in textbooks. So what they do is they will construct a bijective function h, they will just flash a function h, and they will show you that it is bijective, and this function will depend on both f and g, just as you would expect it. But I want to actually try and give an intuitive way of how to construct the function h. So the proof that you will see, if you want to refer to it, is there in the textbook, Elements of Set Theory. But not in the way it will be done now. I was just trying, maybe we should like unearth the proof, right? Instead of just showing you what the bijection is. So if you just want to see what the bijection is, you can go ahead. And some more examples of these kinds of things you can find in. There are so many exercises, especially with these intervals. You can just play around. It's chapter 2. Okay, so to do this, we will go back to what a mathematician named Hilbert did. So Hilbert developed a thought experiment, which is called the Hilbert's Grand Hotel. And most textbooks, when you read countable sets or uncountable sets, this hotel naturally appears. So what's the hotel? It's a grand hotel in the sense that it has, yeah, it is found in his thesis is what I think. Though people say that when Schroeder was on leave, like when Bernstein was on leave, Schroeder proved it or something. But the proof of it was first found in his thesis, Dedekin's thesis. That is true. But I don't know why it's not credit is not given to this. Maybe because he himself wrote in his thesis that it was done. I'm not very sure about the history, but yeah. So this, whatever I said now is with respect to the comment in the chat. Okay, so there is this grand hotel that has lots of rooms, right? It has like infinitely many rooms, and guests keep coming. So there are so many rooms, countably infinite many rooms. And it can also occupy. They can also allow rooms to countably many guests. So whatever examples we have seen so far can actually be completely replaced in the language of Hilbert's Grand Hotel. For example, they say that like all the rooms are occupied by like guests, and then there is a new guest coming in. Like how do you give him a room? Like say rooms 1, 2. So there are rooms 1, room 2, room 3, and so on. There are infinitely many rooms, and then there is a guest G who walks in, and the receptionist has to allot a room to him. Okay, so what does he do? He just asks every guest currently occupying a room to move to the next room and occupy and allots room 1 to the guest J. This is exactly similar to what we have also seen. We just want to create a bijection between the set of guests and the set of rooms, which is the set of natural numbers and so on. So most questions that we've seen so far can actually be rephrased in this language. But this language might be more useful here. So there are many interesting questions in Rosen that you can solve. Like for example, if some of the guests are tired and they say like, okay, I want to move to the next room or to any other room, then there is a huge bus with countably infinite many guests coming in. How will you allot them? Right? What is the bijection? And so on. So these things you can try.
How to prove that if uncountably many persons come in, then there would be no place in the hotel. Uncountably many persons coming.
Because the number of rooms in the hotel is exactly equal to the cardinality of natural numbers. Reals is
yes, but can't we like prove from that no bijection exists, something like that? But this algorithm.
Yeah, there is no surjective function between the set of guests if there are uncountably many guests and the set of natural numbers.
If we continue this, like if there is, we can't order that. Okay.
Yeah, okay. You cannot order them, right? But natural numbers you can. We will see those things. Yeah, but so whatever we said so far, we can actually rephrase in this language, but I chose not to do it. It will be like something we are doing just to motivate. But here it is actually helpful to prove this theorem, or this way of looking at it from the view of hotels is actually useful. Okay, so because I will need some colors. Okay, so we have some rooms and we have some guests here. Okay? So let me put some guests here and also some rooms. So the A and the B that we have, right, in the statement of theorem. Okay. So A will denote the set of guests, and the set B we will use to denote the set of rooms. So now A, we know that there is a function f that map guests to rooms. We will just do it. It is injected. So there are arrows like this. And we also know that there is a function g that maps, okay, there is something for it also. For this one also, maybe somewhere here. And there is also a function g, which maps rooms to guests. Something like this. They look similar. We hope these don't look similar. Do they? I don't know how it displays on the screen. This is. So this orange is the function g, and the violet one is the function b. So what is the function of do? It allots guests to rooms, and what the function g does is it takes every room and it says, okay, this room you take, this room you take, and so on. So let's begin with the function g. So we know that g is an injective function. The goal is to construct a H, which is a mapping of rooms to guests and vice versa. That is a bijection. So we know that G is injective, but it might not be surjective. So what does that mean? This means that there can be guests who do not have rooms. Okay? So G is injective. If G is also surjective, then we are done. The H is the G. So we can assume that to begin with, both F and G are not surjective. Okay? So because G is not surjective, we know that there are guests not allotted rooms. By the function G. Right? So for example, let's look at this question. Let's have, so for example, this just put a couple of numbers here. Yeah, they all like have arrows here. It should be 1, 1. So they have some arrows, but there are these guests, right, who are not allotted rooms by the function G. So what do you do to them? Can someone say what we should do, like in the most natural way? I know that these set of people don't have rooms as per the function G, but I must allot rooms to them.
Use F.
Yeah, so you have to use F to allot rooms for them. You do know that there is an F, so definitely these guests were mapped to some groups. Right? Okay, so now this, so what should we start with? Let's look at the set A minus the image of function B, G. Let's call this set AZ. So these are the guests whom we have to allot rooms according to F. Is this clear so far?
And what is G of theta?
G of
Theta, A minus G of theta.
Oh, there's G of B, where B is the set of this.
Oh,
B is the set of rooms. Oh, okay, so was this not clear? Okay, so B is the set of rooms, and you know that there is a function G that maps the orange one. So these things, they just map rooms to guests, right? Because this function is not subjective, you know that there are some guests who are not allotted rooms. So by G, there is no yellow line here. So you have to allot a room to these guys to ensure that there is a bijective function, right? But you know that there are orange lines, which are the function F, which maps the guests in this set to rooms. This green highlighted thing here is actually the set A0. So you should begin to allot rooms for those guests who are in A, but they are not allotted rooms according to G. Is that clear?
that's not.
Okay, so someone had suggested that we can use F to allot rooms for them. So if you look at F, right? So this room is allotted to this guest here. Is it okay to just allot him here? So let's call this because he's in the set capital A. So what if I just allot this room off to him? What is the issue?
That room is already allotted.
Exactly. So that room might be occupied by someone else, right? And who is that someone else? This person. Right? So what you have to do is, okay, so one thing you can try is I will allot A0 to this room, but there was someone occupying this room. So who is that? This person. Let's call him A1. Where should A1 go now? To wherever F sent you, right? And this adjustment you can keep doing. Whenever somebody rings the calling bell, you tell them, okay, so this person gets displaced to another room as defined by F. Right? So you could actually assign F of A0 to be the room for A0. Right? But then it already has a guest, and who is that guest? G of F of A0. Is the guest currently occupying the room. So he needs to be displaced. The room F of A0. Right? So this person needs to be displaced. So now we have to define a set of guests who are displaced in the first set, first lot. So the set A1 is G of F of A0. I should have written this way, capital A. So you are going to assign rooms to guests in the set A0 to this person. Currently, there are 3 people. And those guests who are displaced in the process are these people. Is this clear? Yeah, you should ask questions. Is it clear?
Yes,
Okay,
ma'am.
so, okay, so in this way, now what you do is, okay, so just like what someone had suggested, now you move all the guests in A1 to rooms, but then those rooms were occupied by somebody. So you have to move them also to new rooms and so on, right? So this way you can define sets A2, which is G of F of A1, A3, which is G of F of A2, and so on. And there are infinitely many sets. In general, an plus 1 is G of F of A. So what does this signify? So these people are the guests who are displaced by our adjustment process. So what we are trying to do is come up with a bijection. In the process, we have displaced a few of them. Not all of them, but some of them. So
I'm
now
only
what?
using small letters for guests.
Sorry?
I'm only using small letters for guests and capitals for sets.
Right. Yeah. So did I mess up somewhere?
Capital A1 is a guest or a set.
So these are sets.
Sets of what?
So you look at all elements in A0, apply F to them, and then apply G to them, we'll get a set.
Okay.
So yeah, maybe I will write it like this. G of 0, A0, A0. Does that clarify?
Yes, ma'am.
Yeah. So the capital A notes are all the set of guests. So A naught is the set of guests who are not allotted rooms in the first level. And in the second level, if you looked at them, okay, so what did you do first? This is like an iterative process, right? You realize that these people don't have rooms. You allotted rooms to them. But in the next level, you found out new people who did not have rooms because they were just thrown out of the rooms that they had. So for example, to allot a room for this A0, you thought, okay, this is the room that he goes to. But there was this person A1 here. You just threw him out of this room and put A0 here. So in the next level, A1 becomes a guest who has not been allotted a room. Right? There are many such people like that. Corresponding to each A0, there is an A1, right? So for this person, there will be another person. For this person, there will be another person. So that is the set A1. Right? So it's F of A0, and then you apply G. That is the person who will be thrown out, right? Who will be displaced. Is it clear?
Yes, ma'am.
Okay. So now these many people have been displaced in our process. And what is it? Entire set of people who are displaced. It's the union of all of this. So infinitely many people. So now we have to construct a function h from A to B using this information. So you have to map guess to rooms in a bijective fashion. In other words, for every x in A, that is for every guest, you have to allot a room. This function should be bijective. So if you looked at this process, some of them may not be displaced at all. Like for example, okay, let me draw one more guest room here, just to make. This is one way this could possibly happen. There could be other ways there. If this is the case, right? G assigned this room to this guest, and F incidentally also assigned the same thing. Right? Because in some cases this could happen. So this person, if you looked at this person, right, he will never be displaced. Right? You look at who this room is occupying, this person, and who's the room, what is the room that he is assigned with this room. So it's correct. You don't have to do anything. So there are some guests who are displaced and some of them who are not displaced. Based on that, we define the function. So your x might be in A tilde, or your x might not be. Suppose your the guest that you pick has been displaced. Right? For example, he is in A0. So what is the room that you allow to him? What did we just do? So you must remember that the image should be a room, right? So h of x is a room, and x is a guest. So this guest is either in A tilde or he is not in A tilde. He has either been displaced or he has not been displaced. So let's say that he is this A0. He's in the set A0 and he's definitely in A tilde. What is the room that you give?
I think we can give f of a naught.
You can just give whatever f given, right? We can do that safely because whoever was here, he will be in A1, and f of A1 is some room. That is what you have to allot to A1. Is it clear? Is this agreeable to everybody? If he has been displaced, you just allot him f of whatever room he should get according to the function. Anybody has a disagreement with this? Is it that clear? I'm surprised. Okay. That is great actually. I thought there will be some disagreement from people. Okay. So whatever room f gives him, just give him that. Now he might not be displaced at all, right? Like this person. Right? Yeah, this, I'll just put this here. But it might be that luckily somehow we didn't get displaced. If that is the case, what would you do? So he is never going to fall in this range, this highlighted one. So there are some people who are highlighted. So this might be A0, set A0, and then in the next step it might be A1s, which are all blue highlighted stuff, and so on. But there might be some people who are never displaced in this. For example, this person. Maybe this person is also not displaced.
Ma'am, I think it'll be G inverse.
Right. So what does it mean if he is not displaced? All right. You actually allotted the correct room to him. Right. So you started with G. And what was G doing? G was allotting rooms to guess. And if it did not get displaced in the process, originally itself he was allotted the correct room. So there is no change that is required. Right? So now what you have to do is, for a guest you are allotting a room. And this room was correctly allotted to the right guest. That is why he was never displaced in the process. So what is the room that this guest who never got displaced gets? Let's say he's the X9 and he is not in X9. He gets G inverse of X. That's what he's supposed to get. Agreed? Or any of you have any doubts? So everybody agrees to this method of assigning rooms to guests. So what we still need to prove is that H is a bijection. That we will take like 5 minutes to do. It's not very hard. But is the adjustment process clear? Okay. It seems great.
Ma'am, I have a question. So there is somebody who is not displaced at all.
Okay.
What if G never? What if that person is also never like reached by the function G?
If he is not reached by the function G, right? Can he not be in A tilde? So A tilde is the set of displaced guests, right? That is you agree on that? So A tilde is a set of guests who displaced. So A tilde is A0 union A1 union all the other sets. Right? So if this person you said was not allotted a room, right? That's what you said by G.
Yeah.
Which means that this is because of the fact that G need not be subject, correct? That is why one of them could be missed.
Yeah.
Okay, so now if that is the case, will he be in the range of G? So this, let's call this person Y, whoever you're saying. Right? Okay, so this arrow should not exist. That's what we say. Okay, this person Y, right? Will he be in G of B? No, right?
No. Yeah. Oh, right. So it'll be an A0. Yeah.
So that is exactly what we mean by set of displaced guests. So everybody will definitely, if he was not in a set of displaced guests, he initially itself he occupied the right room, so nobody will disturb him.
Right. Yeah. No, I got it. Yeah. I forgot what A0 was. Yeah. Thank you.
Okay, great. Yeah, please ask questions. I'm very surprised actually. This is the first time we're seeing it, and they're like very convinced that this is okay. Yeah, but if it was already clear, then it is fine. I don't want to confuse more.
Ma'am, so if it belongs to A1, if it belongs to AI, then it cannot belong to AI plus 1 if a particular element, right?
That is right, because he would have been allotted a room, right, in the previous round itself.
Ma'am, so like, can there be like cycles, like if X belongs to AI, then will it belong to, can it belong to J, if J greater than I eventually?
So can you be displaced again, is what you're saying?
Yes, ma'am.
So if he's in AI, in the ith step, we will just put him in room f of AI,
Okay.
right? So then he's gone. Like no more trouble for him. He can just go sit there. He can just sit here. We won't disturb him further.
He won't
Because
be
in the next round, he won't be in A2, right? So in that round, we will only care about people who have not been assigned. Right, exactly. Yeah, in the language of injective functions, that's what we say. Right. But in the language of hotels, this is what. Is that clear?
Okay, okay.
Okay. Okay, so now what remains is we have to prove that this function is actually a bijection. Actually, I think you can prove this yourself, but I will just give the high level. First thing you need to show that is injective. That is, if h of x is equal to h of y, then we want to show that x is equal to y. Okay? So you could try like 3 cases where x, y are both displaced. Okay? If this is the case, then you look at h of x, h of y, then you know that this is equal, means that f of x is equal to y, but then f was injected. Okay? So x has to be equal to y. And the other case could be that one of them is possibly like displaced, the other person is not. So let's say x is in, but y is not. And what can we say about h of x equal to h of y? This means that by definition, because x is in A tilde, right, h of x is f of x. So f of x is equal to g inverse of y. So this means that y is g of f of x. Right? So y, so what is the set that y should be in? Right? We know that this x is in A tilde, so this means that he must be in one of these sets, right? In one of the AIs. So we know that x is in AN or some n. So what is the set that y is in? Just by definition, from the way we defined these sets A1 to AN.
AN plus 1.
AN plus 1, right? So then this means that y is in A tilde, which is a contradiction. So it must be that x is equal to y. That is, this case cannot occur, right? One of them being displaced, the other being not displaced, but the function h alone is equal. The other is also an easy case. Maybe this you can try as an exercise. Both of them are not displaced. So this just follows because g is injected, right? Then in this case, if h of x is equal to h of y, then g inverse of x is equal to g inverse of y. Inverse of injective functions are injected. That is something that you must use here. So as usual, showing injectivity is easy. Showing that a function is subjective is the hard part. So we need to show that h is subjective. Right? So what does this tell us? So this tells us that there are no two guests sent to the same room. From the injectivity, you know that no two guests occupy the same room. That's what this tells us. Now to show that h is subjective, what we need to do is for every element in B, we need to show that there is an X in A such that the image of X under H is Z. I mean, because we know that H is a function from A to B. So just like before, we know that there is a function G, right, from B to A. That's the function that we started with. And we know that Z is in B. So let's look at the image of Z under G. This is some element of A. This belongs to A. Let's just call this X. So now, what does this mean? That there is one person here. We look at his image under G. And so this is X. We call this image X. Now this X could either be displaced or he might not be displaced. In the process, he is a guest. So he could have been displaced or not displaced. So suppose X is not displaced. So what can you say about H of X? By definition, it is G inverse of X. Which is what? Z. So if he is not displaced, then there is nothing to show. Right? The only case is when he is displaced. This person X is in A tilde. That these things actually you could have tried by yourself. So if he is in A tilde, we know that definitely X is in AN or some N. Now the question is, can it be the case that N is equal to 0? Can N be equal to 0?
No, because those were the
No.
ones that didn't have any rooms in the first place.
Right, correct. So what is he trying to say? Suppose N was equal to 0. Then what do we know? Right, X is in A naught. This means that X is in A minus G of B, right? The way we define the set A naught. But we know that X is equal to G of X, Z, and Z is in B. Right? So this definitely tells us that X is in G of B. So it can never be the case that N is N be equal to 0. So definitely N is greater than 0. So if X is in A tilde, then X is in AN, some N greater than 0. So now we can define, it is valid to define, look at the set AN minus 1. Okay? So AN minus 1 is valid. So we know that X is in AN. This means that from the definition, it is in G of F of AN minus 1. This works because N is definitely not equal to 0. Right? So what does this mean? This means that it is in G of F of X prime for some X prime in AN minus 1. So by definition, we know that Z is G inverse of X. And okay, so this should have been equal. So X is G of F of X prime, which is F of X prime. And we know that X prime is in AN minus 1. This means that X prime is definitely going to be in the set A beta. Then by our definition, what will F of X prime be? Be the same as H of X prime. Okay? So this means that Z is H of X prime. Right? So for Z, there is a pre-image X prime such that the function H maps X to Z. Right? So therefore, H is H. Yeah, but this injective and subjective, I'm sure you could have shown even if I didn't do, but I just wanted to ensure that it's clear. Right? So this whole thing you can actually define in the language of this. In fact, all the proofs that we did, you can actually define that. For example, like the rooms 1, 3, 5 are all occupied, and then there are countably infinite many guests coming in. So what do you do? So showing that the set of positive integers is countable, the set of rationals, all of this could actually be defined in the language of Hilbert's classification. And there are some very nice exercises in those, and so we encourage you to try them. In the sense that, for example, some of the guests are very tired and they don't want to move to other rooms. For example, you cannot displace them. Right? What can you do if another countable infinite many guests arrive? Right? Without displacing. So these people are like high priority. You should not disturb them. You have to somehow displace the other guests and find rooms for these people and so on. So there are many such creative questions that you can try. Showing that this can be done is exactly showing that some set is countable because there are countably infinite many rooms. So yeah, this is what I wanted to say about the Schroeder-Bernstein theorem. This theorem is generally useful. So even if you're asked to show that some set is countable, you can independently come up with two injective functions, then apply this, which might be much easier than coming up with a bijective function. So are there any questions about this statement or proof?
Ma'am, so the same theorem holds for uncountable sets, right?
Yeah, we actually don't use countability here. Okay, so yeah, I should have actually said that. Maybe I think one place we are using countability is this one, that each AI is actually countable. Right? And the union of countable sets is countable, so A tilde is countable. This is something we won't have if the sets are uncountable.
Why do we need that AI is countable?
Yeah, I'm not sure if you need it, but that is one thing that's the only difference with where countable and uncountable come. So that's I'm just trying to see if there is any other place.
Okay.
It doesn't seem like, but I haven't thought about it. So I will try to see. Yeah, I don't see of any other place where you might need
Okay, ma'am.
countable sets. Yeah. I mean, if at all, it would have come here. But so this generally does not assume anything about the sets A and B, the statement. Yeah. Let A, B be any sets. That's right. So I did not use countability at all. A, B, B, any sets. That's right. Yeah. We did not use countability here. It's just that it's used to prove that some sets are countable. That is right. Yeah. Because we did not use the fact that A tilde is countable anywhere, as far as I can see.
Okay, so the picture was just for intuition.
Yeah. So if I otherwise, what could I have done, right, to convince you that this process is right? I could have just like described the function h and then proved that it's a bijection. But then you won't have any clue, right? Why h is defined the way it is. Yeah. So the proof in Herbert and Rutten is just like half a page. It just gives you this. It just tells you there is g, there is f. Consider h, and this is a bijection, and then the proof that is bijection. Yeah, I thought that might be deceiving in a class, right? I cannot say that. Flash a function and say that it is bijection. So that is why I just thought of describing it this way. It's not necessary that you look at this proof from the Grand Hotel way, but I think it will be useful. It would have been useful. Right? So in the sense that you yourself came up with the function h, right? I did not tell you what h is. Yeah,
Yes,
it is
ma'am.
just for classroom teaching. It's not necessary that you prove things via this Hilbert Hotel. It's easier to see a function that is all. So the proof in most text or any textbook would not probably go this way via the guest room thing, even in Ender. He just says that look at the function h, consider this function, this is a bijection. That's all. Okay, this is all that I have to say. Was thinking about proving well ordering, but I'm not sure if Partha might have some combinatory stuff to discuss now. There are like 20 minutes left. If I do well ordering, then it might take 10 minutes. Partha, are you around?
Yeah.
So do you think, I'm not sure, like, is there anything that you can start now and it will be fine? I can
Yeah, I mean, I have like 20 minutes. I can start something
okay.
on the
Then
combinatorics.
yeah, we can do well ordering it. Okay.
You are continuing on the while ordering?
No, you can probably do that.
Okay.
You can
Okay.
start. I'll just stop recording.
Okay.
Or shall I just continue recording? We can just I can just upload it. That's also fine.
That's fine. Yeah.
Yeah. Okay. So I will just stop sharing.
Yeah. Thanks. Give me just a few minutes. Settings. Can you see the screen?
Yes.
Okay. Okay, so after this nice introduction to set theory, so let's get back to some more into combinatorics. So today we'll start with one of the most important topics in combinatorics, that's called partitions. So these kind of problems are all around in combinatorics. So I'll give you an introduction as always, like by solving some problems, some examples, and then when we study generating functions later, then you will see a more like analytic approach to solve these problems. But at the moment, we'll just use our basic intuitions to solve the problems and we'll define them and go on. Okay, so I think most of us seen partitions in some time in our life. So let's, so there will be variety of problems. It's important to know their difference and they're nice. Okay, so let's start with some examples. So let's start with the problem. Okay, so we have n identical balls and k distinct boxes. We want to partitions the balls. That means keep the balls in the boxes. How many ways? We can do that. So this is one benchmark problem or problem around this question in combinatorics that occurs in various forms, and that's what we are going to discuss. Okay, so since boxes are distinct, so let's say that A1 is the number of balls that goes into the box 1, right? Similarly, A2 is the number of balls that goes into the box 2. So blah, blah, blah. So AK. And they must add to N. So we want to decide how many ways we can choose these numbers. So that the sequence of numbers A1, A2, AK, they adds up to N. Right? So let's define, so if AI is a greater than equal to 0, in particular, some of the AIs could be 0, then such a decomposition of N, we just give it a name, weak composition. And if each of the box contains at least one element, then either we call it strong composition or just composition. Okay, so the first question is that Is this color is properly visible? Like, are you feeling it comfortable? I can change the color.
Yes, sir.
Okay. So number of weak composition. So you got the difference, right? Weak means some of the boxes can be empty, and the strong means each box should contain at least one ball. Okay. Okay, so let's see how we can attack these questions. So if I
Permutation with
place,
similar objects.
sorry,
Permutation with similar things.
yes, that's right. So do you know, do you have a full answer of it?
N plus k minus 1 6 n.
Right, so I think you have already seen it, right? Okay, so some of you may have seen it in some IIT preparation or somewhere, but I have to do it because this is fundamental. So if you have, there are variety of ways to tell this. So let me place k minus 1 stick. So what are the sticks are doing? They are basically the boundary wall of the boxes. That means this is like a first box, this is the second box, third box, and this is like kth box. So if you place k minus 1 as sticks, you have k boxes, right? So now, so these are my balls. So these are n balls, right? So these problems could look easy to the people who have already seen it, but people who are seeing it for the first time, it may not be that easy. It may be tricky and you may get lost into long calculation if you don't take the right approach. So it's important to learn it. So these are like n balls, they look similar. So now what is the point of having these sticks, right? So basically if you place the sticks in the balls, then you arrange these balls into the boxes. Can all of you see that? I can place this k minus 1 sticks anyway inside these balls. And it is not necessary that all the between two sticks you have to always place a ball, because it could be empty, some box. Right? So if you think for a moment, these questions are really nice if you think in a right way. So this is like total objects, total number of objects that we have is n plus k minus 1, n balls and k minus 1 sticks. But the sticks are identical, balls are identical, and you have to arrange them. That means you have n plus k minus 1 object in which n objects are identical, k minus 1 objects are identical. How to place them? That's the question, right? Now from our 10 plus 2, we know that number of such arrangement is n plus k minus 1 factorial by n factorial k minus 1 factorial, which is same as n plus k minus 1 choosing. Right? This is not difficult. And now imagine that this does not prohibit that some box could be empty, right? We allow some box could be empty because two things can come like side by side, two sticks. So this box that is shown by these two sticks is empty. It does not contain any ball. So this is the number of weak compositions. And what is the strong compositions? Again, it's very easy. So let's count the strong composition. Strong composition means we have again n balls. n balls, and none of the box should be empty, right? Then how do you do it? Someone should try who has not seen it before. I mean, if you know the solution, then it doesn't matter. But if you have not seen this problem, I invite you to try it.
So n-1 sec SAN.
But you have seen it, right?
N-1
Then you have seen the problem. So if someone has not seen it, it will be good to try. See,
also,
if I
also like there is a solution from the multinomial. I mean, yes, from the multinomial.
Step by step. So there will be many variants of these questions. So let's allow the others to see it who has not seen it. So that means, suppose I place the sticks here, 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 for example. That means, see, there's none of the sticks, none of the boxes that the sticks shows is empty. So this box contain 1, this box contain 2, this box contain 3, and so on. That means if I choose these gaps between these n balls are created, these are like n-1 gaps. If I place the sticks in those gaps, then I'm done. I have to choose those k-1 gaps from those n-1 gaps that these n balls have created, right? So number of strong composition n-1, choose k-1. Yeah, some of you may be trained in some camps or IIT preparation, so you probably have seen this kind of things already, but it is not usual to see it in just your 10+2 syllabus. So this is good to do these things. And yes.
Can't we do this with just starting with, since there's k boxes, we just put k balls in the k balls, 1 in each box, and then do the same.
Sorry, you did not complete.
So there's k boxes.
Yeah.
So we can start off with putting 1 ball in each box, and then doing the same thing of weak composition.
You put one of the boxes, but how do you are saying that let's put k balls in the boxes, and you have n-k, and for n-k you are doing the, I think it will be same thing probably. Yeah, you can do that.
Okay.
Yeah, but this is much simple. You just choose these boundaries and you can get it, right? Okay. So yeah, there could be many arguments. You have to just be careful that your argument is correct. I mean, this is just one argument that I'm writing. There could be many arguments. In fact, later you will see a lot of arguments can be framed in more analytically, like a generating function, where you don't need too much think. You have to just calculate a few objects and you get the answer. So like a more like a systematic approach of these things. Yeah, there could be many equivalent arguments. And so an immediate corollary is that for the number n, the number of compositions. When I say that number of compositions, mean it could be composed in any of the k ways. I mean, k could be 0, and k could be 1, k could be 2, and k could be at most n-1, like that.
Sir?
Yes.
So could you just like repeat the boundary argument once? I think I missed it.
Sure. So you mean that composition argument, right?
Yeah, like strong composition.
Strong composition. So these red dots are the balls. So they are identicals. Now, if you forget about these sticks that I have drawn here, so they have created like n-1 gaps, right? These n balls.
Yeah.
And now, if you place the sticks in any of these k-1 gaps that these n balls have created, then you are done, right? Then no box will be empty. For example, I have placed this tick here means first box contains this red ball.
Yes, I understood.
Right. So from this n-1 gaps, you have to really choose the k-1 position for the sticks and you place them. Right?
Yes, sir, thank you.
Yeah. So now the corollary is that for the number n, that, so let me just, actually I'm a bit new to this particular software. I'm not used to of it. The number of compositions is by the same formula. n-1 choose k-1, k runs from 0, that's equal to 2 power n-1. Right. So let me state a simple exercise. A simple exercise. So count the number of compositions of n into, let's say, 5 parts, such that each of them is at least 2. So this is like the argument someone just said, to use first, you assign some balls and then use the weak principle. If you think around these ideas, this exercise you should be able to do easily. So this is an exercise that you try offline. Okay, so let's continue for more examples. So it is very important to remember the setting, right? So far what we have done, the balls are identical and boxes are distinct. Actually, I don't have much time. Maybe I'll just introduce one problem and then you have to stop. Okay. So the next question is set partitioning. As I told you, there will be various settings. Like sometimes balls will be distinct, boxes will be identical, both are identical, all such things will come. So set partition. What is a set partition problem? So you have a set. This box n means this is the set of numbers 1 to n. Okay. So they are distinct, of course. I mean, they are numbers 1 to n. And the goal, partition them into k sets. So that is k boxes, all are identical. So what is the problem? For example, like, I mean, if you have 1, 2, 3, 4, 5, so you can partition it like 1, 2, 3, 4, and 5, right? This is like a 3-box partition. So obviously, when you say that partition that set into sets, you don't, I mean, you don't count them like order. It is really like a set partition, right? So whether I mean, this is same as saying that's 2, 3, 4, 1, 5. These two partitions are same because this is a partition as a set. So that's why I said that the boxes are identical and the numbers are, of course, different. They are like 1 to n. Is it clear?
Yes. I have a solution. I'm not sure whether it is correct.
You have solution?
Yeah, for this problem.
For which problem?
Idea.
You want to count the number of partitions?
Yes, sir.
Okay. But just to make you, just to alert you, there is no closed form known for this problem. closed form is, I mean, this number does not have a nice form, like it is not a very closed number, like it has a big long expression, but nobody knows a very cute closed form of it. I mean, for example, this is not like n power k or k factorial or n choose k, nothing like that. There is no nice, so if you are finding a closed formula, then you have to go back and think what is flaw in your argument.
Yes, sir.
So that's like I need to alert you. Okay, so this number is nk is basically this number of partitions of 1 to n into k boxes. This was first studied by Stirling, and this is called Stirling number of first kind. Okay, so let's check a few basic things before we proceed. For example, S in K is obviously 0 if n less than K, definitely. So here when I say K boxes, you should really mean that no box is empty, because in a set theoretically you are partitioning into K sets, means it is in the K sets, like this is like a 3 partition, right? So when I asking you to partition the same question in a different language, like partition them into K boxes, means no boxes goes empty. I may specify that in the exam paper also. Okay. And what is ace of n1? This is clearly 1, because there is only one way to place all the balls in one boxes. Ace n is also 1, right? Because none of the box should go empty, and you have n numbers, so you just give one number to each of the boxes. Boxes are identical. And what about this one? Ace of n minus 1. You have n minus 1 boxes, right? And you have n numbers, 1 to n. None of the box should go empty. That means one box will get 2 numbers, right? And the rest of the box will get 1 number. So you just choose 2 numbers who go together, and then the rest is determined. That means, interestingly, this number is just n choose 2. Okay, so someone was telling about some idea of finding this number, but this is not easy. You will later see how to find a nearly nice form of these numbers. But let's do a simple recurrence relation. Recurrence means let's try to prove this identity. Snk equal to S n minus 1 k minus 1 plus k s n minus 1 k. So see, this is called a recurrence relation. We have not introduced recurrence relation formally, but maybe you have already an idea. Solving that problem for nk with the help of solving the problem of the lower value. So here you have solved like n minus 1 and k minus 1. This is like some kind of like an induction. If you know the solution for the lower values, then you can maybe cook up a solution for the higher value. And here you know the solution for n minus 1k, then you can cook up and write the relation for snk. Yeah, and this is very useful, thinking in this kind of recurrence ways. So let's try to understand why this is true. So you have these numbers, right? 1, 2, 3, up to n minus 1 and n. Right? So what might happen? How can we partition S, N, K into K boxes, identical boxes? It may happen that, so either of these cases can happen. It may happen that the number n goes alone. It just goes to one element set. It does not take anybody with it. right? And then how many ways it can happen? So you have to place that rest of the n-1 elements in k-1 boxes. So that can happen in S of n-1 k-1 ways. By definition, right? This is the definition of the function Snk. What is the other thing can happen? Like these n-1 elements are already placed in k boxes. Then the element n comes and select one box. What is the solution for that? Two things can happen, right? N prefer to stay alone. Right. Sorry, say it again. Who said? Nilabja.
Sir, yes, sir. I mean, the n element can go to any one of the k boxes.
N-1
So it
element.
has.
You mean n-1 element, right?
No, sir. I mean, n-1 elements have been arranged in k boxes, right?
How many ways you can do that? That's like
that is S n-1k.
Right, by the definition.
And the nth element is placed, has k options. Actually.
Exactly. So this is like, as is correctly said, k options. So k times this. So that gives the recurrence. So these are the two possibilities that you can have. But Snk adds up to these two things. Okay, so I don't think I have time. Okay, so let me stop here. Maybe it's already 6:25. Continue from this next class.
Thank you, sir.
Thank you.